Okay, this is a lesson on 4.7 scientific notation. Now, scientific notation is a shorthand. I should probably make a hyphen there. It's a shorthand we typically use to express very large or small numbers such that we don't have to write out all the zeros. So how does it work? Well, a number is written in scientific notation if it has the form C, that's a C right there, times 10 to the nth power. So it has to have some number times 10 to the nth power, where this number C, and that is a funny name called a mantissa, is a number that has to be greater than or equal to 1, but less than 10. All right? So let's look at some problems and see how that works. So one way we can look at this, we look at standard form is just the normal way of writing numbers. Product form is making the number a product of a number times a multiple of 10. So in this case, I'm going to move the decimal from right here all the way over to right there. So that's 5 places. So I'm going to make this 7.25. And remember that these numbers are equal. And I'm going to say times the number of decimal places so that this still equates would be 10, would be times 10,000. Okay, so that would, if I multiplied 7.25 times 10,000, that would move the decimal place back to where it started, those 5 places. Now 10,000, we can convert to a power of 10. We know that's 10 to the 5th. So now I've successfully expressed this number in scientific notation that started at 725,000. It exactly equates both of these, but this is the scientific notation version. Now, when you're looking at a number very small, this one has 5 zeros after the decimal, 6 zeros if I count the one in front. But what I'm really doing here is multiplying this by, so this is 6 times 1/10, 100th, 1,000, 10,000, 100,000, million. So I'm multiplying it by 1 over 1 million. All right. Now remember that 1 million is 10 to the 6th power. So, but expressed as 1 over 10 to the 6th power is 10 to the negative 6. So I'll make this 6 times 10 to the negative 6th power. So what I've done is slip the decimal 1, 2, 3, 4, 5, 6 places. When you do that left, it becomes a negative exponent. Now, what if I wanted to say what a number in product form is in standard form? Well, that would mean multiplying a number by 10,000 would be sliding its decimal 4 to the right. So that'd be 1, 2, 3, 4. So that's 41,000. All right. And then in scientific notation, this would be 4.1 times 10 to the 5th power. Because I've slid the decimal over, I'm sorry, that would be 4 to the 4th power, because I've only slid the decimal over 4 places, okay? And let me get that just right, how we want it. So to the 4th power, okay? Now, how about this one? So I've multiplied this by a decimal of, and this could also be thought of as tens, hundred thousands, 10,000s, 100,000s, millions, 10 million. So this could be like 7.23 over 1 over 10 millions. So however many zeros I'm sliding this is going to become a negative decimal. So 1, 2, 3, 4, 5, 6, 7, right? That would make it times 1. So it's going to be 7.23 times 10 to the negative 7th. And over here, when you multiply this by this amount, so this would be sliding the decimal. I would have, since I have this many zeros, I would be sliding it 7 places to the left. So I'd want to have 7 overall zeros. So 1, 2, 3, 4, 5, 6, 7 before that 7 shows up, right? So working backwards, one way you can verify is that this would be 1, 2, 3, 4, 5, 6, 7 right there, and that put that decimal in the right place. So about 3 billion 50 million. So I'd want to make that 3.05 times 1 billion. So I'm going to need 9 zeros there. And that would be, so that's 9 zeros, so 3.05 times 10 to the 9th power, okay? Very large positive number. How about 9.2 times 10 to the negative 4th? Well, let's, over here, this would be, kind of 1 and then 4 zeros, so that would be like if you had 9.2. Well, that would be sliding your decimal 4 places to the left. You would need 4 zeros overall, counting the one before, and then here comes your 9 and your 2. So that's what it looks like in standard form. Now, how about a word problem? Let's look at the average distance from Mars is from the sun. Again, remember planets revolve around the sun in a oval or an ellipse, so that's not always the same distance, but the average distance is 140,600,000 miles. So write this number in scientific notation. So so I can take 141,600. I'm going to move my decimal place 368 places to the left. So this is 1.416 times 10 to the 8th. Let's go ahead and use our units here since it's a word problem. All right, and then the average of a quarter-ounce gold American Eagle coin is 0.022, so 22 thousandths of a meter. That's the diameter. Write this in scientific notation. So I've got 0.022. I want to slide this 2 places to the left. When I'm doing that, I'm really saying this is equal to 2.2 times 10 to the negative second. And this is meters. So it's a fraction of a meter. That's why I don't add an S there. All right. Now let's put some numbers in scientific notation in order. So you have 5.3 times 10 to the 5th, 520,000. So I think I'd like to leave these in scientific notation in order to do this. So let's get this one in scientific notation. So this is 5.3 times 10 to the 5th. How does that compare with, this one's going to be 5.2 times 10 to the 5th. So obviously 5.3. Now how does that compare to 7.5 times 10 to the 4th? Well, for 2 reasons. The power of 10 is bigger, and this number. We might want to get them on the same, well, actually, I'm sorry, this is 10 to the 5th over here. So it doesn't really, all bets are kind of off here with the powers being bigger for, oh, that's a 5. That is a 5. So let me back up. Sorry, can't read my writing. So the 7.5 times 10 to the 4th has got to be smaller than these other numbers, even though their number preceding the power of 5 is bigger. And if I want to, I don't think I really need to do that, but from least to greatest, this is going to be 7.5 times 10 to the 4th. Then I'll have 5.2 times 10 to the 5th, and then I'll have 5.3 times 10 to the 5th. So if I want to work with the original numbers, I'd say this one, then say 520,000. I'm sorry, that was the 520,000, this one over here. Nope. No, that's this one over here. That's the 7.5 times 10 to the 4th. All right, then I'd want to have the 520,000. That's this one, just because I'm writing them in the original, so I use semicolons here. And then 5.3 times 10 to the 5th. That would be least to greatest. Now it works the opposite with smaller numbers. The ones further away from 0 are going to come first, but let's get them all in scientific notation. So you have 4.5 times 10 to the negative 4th. You have, this one's going to be 4.8 7 times 10 to the 1, 2, 3, 4, 5 times, so times 10 to the negative fifth. So that's going to definitely make that one the smaller, and then you have 4.8 times 10 to the negative fifth. So smallest one is going to be this one, so you'd have 4.8, well, let me just do a 1, 2, 3, how about? So this would be your smallest one would be your 4.8, because this number is actually, I'm sorry, with I don't want to confuse this with negative numbers. The smallest number here is the one with the lowest mantissa, or the number that precedes the power of 10, that with the smallest power of 10. So 4.7 times, so I told you I was going to write a number to put them in order. So let me do that. So let's say this one is the smallest, so it would be 1, and then this one's going to come next, and then this one's closer to 1 than, or these two are closer to 0 than this one, because negative fourth just means it has one less 0. So so this is going to be 3. But really, to see this, let's look at these numbers. So this one over here is equal to, I'm going to have 4 total zeros, 3 after the decimal. And then this one is 0. I've got 5 total zeros. Right, and this one's equal to 0.00048. So this one's the smallest. Again, 1 smallest, second smallest, and largest. Okay? Now the volume of a 1 mole of oxygen is about this. It's a very small fraction of a cubic meter. Find the volume of this many moles. So, you know, this would be like if I have a beaker of water and I say it's got this volume. Now I have 10 beakers of water, so or 50 beakers. So I'm going to, however much volume is in my original container, and my container here is a mole of oxygen atoms, and then I have this many moles. So I'm going to do 1.5 times 10 to the fourth times 1.736 times 10 to the negative fifth. Well, the smart thing to do here, you could use your calculator just to multiply this all together in scientific notation, but I'm going to, since this is just a string of items being multiplied, I can put my non-powers of 10 together with my powers of 10, and then put my powers of 10 together. And I have this calculated on a sheet here. So those two multiply together to get 2.604. The powers of 10 I'll put together over here, and we can do those without the aid of a calculator. We add the exponents, so 4 plus negative 5 is times 10 to the negative first. And so that's the volume of, so obviously the volume is much greater because you have a whole lot of these moles. So that, again, volume would be fraction of a cubic meter. All right, so let's look at some more multiplying like that. You don't need a calculator to do these, so we're just going to put the non-powers of 10 together. So that's 2 times 2.5, which is 5, and then I put my powers of 10 together. So this is 5 times 10 to the, add the exponents, 10 to the 8th. And then I have 1.5 times 10 to the negative second times 4, so two small numbers. Put the two non-powers of 10 together with the, and then put the powers of 10 together. And this is 1.5 times 4, well that's 6, and then this is 10 to the negative 6th. But add the exponents right there. Okay, and that's the end of today's lesson.